here, here. Let's try to find out the major pointer. I might have. Voila. This one, right? Lambda 1 is equal to, I associate this lambda 1 is equal to 1 with the ultimate base hat lambda 1 is 1 over square root of 2, 1 r, right? So actually you can solve this eigenvalue problem and to find out this eigenvector is the same, right? So what happens? I didn't stop. Let me see. I think accidentally I pushed the stop button somewhere in the middle of class. So if I upload to YouTube, some portion can be just dumb. I don't know how to. I am not the professional YouTuber, so I don't know how to put the recording back. So unfortunately, I don't know. I hope it's not too long, but I just found out some portion is. I just stop the recording button. It's called the Murphy's law. If something is going to go wrong, it will go wrong. So let's say example sigma y is a 0 minus I 0. We know that we have checked that this matrix is Hermitian. So A lambda is lambda A lambda. So determinant minus lambda minus I minus lambda is lambda square minus I lambda square minus 1 is equal to 0. So lambda is again plus 1 and minus 1. So familiar, right? So when set lambda 1 is plus 1, again lambda, maybe you can say x and y, and in this time x and y can be complex. Somehow I have a feeling that they are going to be complex number. So A times lambda 1, 0 minus I 0, xy is xy. So x equal to minus y, I, or ix is equal to y. So we can simply set lambda 1 is x, ix, and that maybe x can be real, you never know. Lambda 1 is x minus ix ix x square is equal to 1. So you can set actually x as a square root of 2, right? 1 over square root of 2. Then small room, lambda 1 is equal to 1. This orthogonal basis is square root of 2, 1i. That's familiar, right? We have seen this before. So I associate this matrix with lambda 1 and this matrix, right? This basis. So we can go back. How about when lambda 2 is minus 1, we can set, okay, lambda 2 as x and y. Then a lambda 2 is minus of lambda 2, right? So 0 minus I 0, xy is minus xy. So y is minus ix. So tentatively we can set lambda 2 as x minus ix, right? But lambda 2, which is x ix, x minus ix, 2x squared is equal to 1. So we can set x is 1 over square root of 2. Then lambda 2 is simply square root of 1 minus I. Minus 1. So for this matrix, again, we associate lambda 1 plus 1, right? And this eigenvector, we call this eigenvector 1 over square root of 2, 1i, x1, 2 is minus 1, lambda 2, so we call this lambda 1, 2 is eigenvalue, and the ket vector lambda 1, lambda 2 is eigenvector. This is just terminology. Perhaps we can maybe stop for a few minutes and continue. Okay, so one student asked me just before during the break that if what happened between the inner product of two different basis functions, such as lambda 1 was square root of 2, 1i, lambda 2 was square root of 1 minus I. Then we can check the inner product. Square root of 1 minus plus I, 1 I, right? So this is obviously 1 over 2, 1 minus 1 is equal to 0. The same as lambda 1, lambda 2. So previous case as well, we don't have to show that, so you can check. So if the matrix is Hermitian, the old eigenvectors are supposed to be orthogonal to each other. The one property is inner product between different eigenvectors is 0. Same eigenvector equal to 1, right? So they are orthogonal to each other, orthonormal bases. Another example is an easy one, so let's do that. Is 0. Example A1 minus 1, 0, 0. This is actually sigma z. This is very easy. So determinant A minus lambda I, lambda right? So this is basically 1 minus lambda minus 1 plus lambda minus 1 minus lambda square is equal to 0. Uh-oh. What? Now you can see that, right? So lambda square is equal to 1. Lambda is plus minus 1. Again. So case number 1, lambda equal to plus 1. Set lambda 1 as AB. Let's go back to AB again. So A lambda 1, 1, 0, 0 minus 1, AB equal to AB. So that means A is equal to A, B is equal to minus B. That means B is equal to, if some number is same as minus of itself, what is that number? 0. Very good. So lambda 1 is A0. So I think we can just set A equal to 1, right? You don't have to, so we can set A equal to 1. So lambda 1 is just 1, 0. We do have a degree of freedom to up to phases, but it's okay. Lambda 2 minus 1, right? So A lambda 2 is minus lambda 2. Say lambda 2 again, AB. So we can say 1, 0, 0 minus 1. AB is minus of AB. So A equal to minus A, B is equal to B, right? So A is equal to 0, B is equal to 1. We can say for lambda 2 is minus 1. Eigenvector cat, lambda 2 cat is 0, 1. So far, everything fits with our previous result, right? Now we are getting close to the actual quiz problem for next week. So say A 1 1 0 1 0 1 0 1 1. The 3 by 3 is definitely for quiz problem, so this is important. I'll say stop. Very important for quiz. So matrix can be different, right? So I'm giving a hint. Can be different, but omission. So let's check whether this matrix is omission. A adjoint. So omission is a transpose complex conjugate, right? So you change the column by row. So you this column into the row 1 1 0, right? And second column, second row 1 0 1. Third column become third row 0 1 1. Oh, voila! It's the same as the original matrix, right? So this is omission. So I will give you a very important homework problem. This is extremely important. Find 5 3 by 3 omission matrices. If you go back to your home or dormitory or find 5 3 by 3 omission matrices. If we are lucky, maybe next quiz will be one of those matrices. You can Google Wikipedia, or maybe you can ask ChatGPT. Find 5 3 by 3 omission matrices. I think ChatGPT is smart enough to produce maybe even 10 or. So I used to Google all the time, but these days when I want to ask something, I also ask ChatGPT sometimes. So for this kind of problem, probably ChatGPT is the best source. Just ask, find 5 3 by 3 omission matrix. Anybody can try that? If we have access to the internet? Is it work? Does it work? You haven't checked that? I mean, ChatGPT. You can ask. So try to homework is find 5 3 by 3 omission matrix and try to reproduce what I have been doing, I'm going to do in my class. So determinant. Let's try to find out the determinant. You need some more time to copy. A prime, A minus lambda I. Okay. Uh-oh. Okay. wrong with that? 0. 됐다. I think Wi-Fi is probably not stable, so maybe I'll just go a little faster because I like to finish before he changes his mind and stop showing the screen. He or she or whatever. So this is 110, 101, 011 minus lambda 00, 0 lambda 0, 00 lambda, right? So 1 minus lambda 1 0, 1 minus lambda 1, 1 0, 1 minus lambda. So you can actually use minors to expand this, right? So I would say choose this, then blah blah. 1 minus lambda minus lambda 1 1 1 minus lambda minus 1 2, right? You delete this and this, you have 1 1 0 1 minus lambda. So this is extension via minor, right? Mij. So this is 1 minus lambda minus lambda 1 minus lambda minus 1 minus 1 minus lambda. So 1 minus lambda, lambda, lambda minus 1, minus 1, minus 1. One minus lambda, lambda square minus 1, minus 2. One minus lambda, lambda minus 2, lambda plus 1, right? Is equal to 0. Sorry. So, what do we have? Lambda is equal to minus 1, 1, 2, right? We have 3 different eigenvalues. So we can set lambda 1 is equal to minus 1, lambda 2 is equal to 1, lambda 3 is equal to 2. So 3 by 3 is a bit complicated as compared with the case for 2 by 2. So probably I'll just make it as slow as possible, but you also have to look at the screen very carefully. So I can continue, right? Case number 1, lambda 1 is equal to minus 1. So let's say lambda 1 is A, B, C. Then A, you can choose X, Y, Z if you like. Oh. I think it doesn't like me very much today. I don't know why. Okay. Uh-oh. Screen went black. Oh. Can you see, right? Lambda 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. Oh. Oh. Let's go back to ABC. A plus B, A plus C, B plus C equal to A, B, C minus, right? So A plus B is minus A. A plus C is minus B. B plus C is minus C. Okay. So 2A plus B is equal to 0. A plus B plus C is equal to 0. B plus 2C is equal to 0, right? So B is minus 2A. B is minus 2C, right? From here, A plus B is equal to minus A means 2A is equal to B. So B is going to be minus 2A, right? And the last one, B plus C is equal to minus C. That means B plus 2C is equal to 0. So B is going to be minus 2C. So what does then tell these two equations? A is equal to C, right? So we can see that A is equal to C. Now, A plus B plus C is equal to 0 means A plus A and B is equal to minus 2A is 0. So lambda 1 is actually of the form. We have A minus 2A, right? So normalization condition, lambda 1 is equal to A minus 2A, A minus 2A, A square plus 4A square plus A square is equal to 1. So what we can choose A is actually 1 over square root of 6. I think screen is still okay, right? So let's say lambda 1 is equal to minus 1. Lambda 1 cat is square root of 6, 1, minus 2, 1, right? How about lambda 2 square root of 6? 1 minus 2, 1. Okay. Oh. Okay. Oh, it's a little slow. I think somehow the buffer is okay. Did I tell you about Murphy's law in previous hour? If something is going to go wrong, it will go wrong. So I think we are just seeing the proof of Murphy's law today. It's kept failing. So lambda 2 is actually screen response is really slow. I think something in the buffer or something in the system is, I think, slowing down. ABC. Okay, good. It's A lambda 2, 1, 1, 0, 1, 0, 1, 0, 1, 1, A, B, C is equal to A plus B, A plus C, B plus C, A, B, C, right? So A plus B is equal to A, means B is equal to 0, right? A plus C is equal to B, B plus C is equal to C, B is equal to 0 again. C is going to be minus A, right? So let's double check before I proceed. A plus B is supposed to be same as A, means B is equal to 0, right? A plus C is equal to B, this is 0, right? So C is equal to minus A. B plus C is equal to C means B is 0 again. So lambda 2 is of the form A 0 minus A. So from lambda 2, A 0 minus A 0 minus A squared plus A squared is equal to 1. A is square root of 2, right? So lambda 2 is square root of 2, 1, 0 minus 1. Of course, lambda 2 is plus 1. I hope the screen is still alive. Next page. Now, can I move on? Still need time to copy? Right, 1, 0, minus 1. And lambda 3 plus 2. And you can say lambda 3 is, again, A, B, C. Then 1, 1, 0, 1, 0, 1, 0, 1, 1. A, B, C is A plus B. A plus C, B plus C is twice of A, B, C. So A plus B is 2A. That means B is equal to A. A plus C is 2B. B plus C is 2C. B is equal to C, right? A. So lambda 2 is actually A. So square root of lambda 3. Lambda 3 is A. A is 3A squared is equal to 1. A is square root of 3. Let me double check before I proceed. A plus B, A plus C, B plus C is twice of A, B, C, right? So A plus B is equal to 2A, that means B is equal to A. B plus C is 2C, that means B is equal to C. So B is common, that means A and C are the same, right? And so lambda 3, 2, and 1. So let's summarize for this matrix. Copy, right? So we are actually in a very nice age, modern age. When I was in your age, not then, right? So when I was in your age, we didn't have iPad, we didn't have a projector. So my professor has to use Blackboard, just write everything and with the chalk. And students usually sit back and then had to copy on his note, on her note. So, but these days we are living in much better days, better ages. So I can use iPad, and you can use iPad, and after the class, I can just upload it to YouTube, and you can watch at home, right? So there's been a big change. It was 1980 when I was a sophomore, so almost how many? 43 years ago, right? I was a student. So this just reminds me of how important the technical progress is, right? Probably you need some is what we have been doing. A. This is Hermitian. We have 3 eigenvalues, right? Lambda 1 is -1, lambda 2 is +1, lambda 3 is +2. And associated eigenvectors are lambda 1 was apparently square root of 1 minus 2, 1. Lambda 2 was 6. Square root of 2, 1, 0 minus 1. Was it? And lambda 3, square root of 3, 1, 1, 1. And let's see if they are orthonormal to each other. So lambda 1 and lambda 2. Square root of 6, 1 minus 2, 1. Square root of 2, 1, 0 minus 1. Square root of 1, 12. What do we have? 1 minus 1 is equal to 0, right? How about lambda 1, lambda 3? Square root of 6, 1 minus 2, 1. Square root of 3, 1, 1, 1. Square root of 18, 1 minus 2 plus 1. Again 0, right? How about lambda 2, lambda 3? So that's lambda 2, 1, 0 minus 1. Square root of 3, 1, 1, 1. Square root of 6, 1 minus 1 is equal to 0, right? So we found that orthonormal basis, right? We just have checked that, right? So 3 by 3, we have just checked that they are orthonormal bases. And now let's check whether they satisfy that the other two properties, completeness and spectral theorem. So we have to form outer product first. So let's see. Still, I can proceed, right? So outer product. Lambda 1, lambda 1, which is square root of 6, 1 minus 2, 1, square root of 6, 1 minus 2, 1, right? So 1 over 6, 1 minus 2, 1, minus 2, 4 minus 2, 1 minus 2, 1. Lambda 2, lambda 2. Square root of 2, 1, 0 minus 1. Square root of 2, 1, 0 minus 1, which is 1 over 2. 1, 0 minus 1, 0, 0, 0, minus 1, 0, 1. Lambda 3. square root of 3, 1, 1, 1, square root of 3, 1, 1, 1, which is actually 1 over 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. So let's check first. Lambda 1 plus lambda 2, lambda 2, lambda 3, lambda 3. 1 over 6. 1 minus 2, 1, minus 2, 4, minus 2, 1 minus 2, 1. So let's use the same denominator because we have to add them together, right? So it becomes 1 over 6, 3 o minus 3, 0, 0, 0, minus 3 o 3, 1 over 6, 2, 2, 2, 2, 2, 2, 2, 2, 2. It becomes, what happens? 1 over 6. If we add them together, what happens? 6, 0, 1, 3, 2, 0, right? 0, 6, 0, 0, 0, 6. 1, 0, 0, 0, 1, 0, 0, 0, 1. Identity, right? So let's try to copy this. Let's see, which one was that? I think this. Copy, and paste. 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 Can you see that, right? I can paste this and check lambda 1, lambda 2, lambda 3. And let's see what happens. Lambda 1 is minus 1, right? So minus 1 over 6, 1 minus 2, 1, minus 2, 4, minus 2, 1 minus 2, 1. Lambda 2 was plus 1, so just 1 over 2, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Lambda 3 was 2, so that's 2 over 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. So let's combine the denominator 6. So it becomes minus 1 over 6, 1 minus 2, 1, minus 2, 4, minus 2, 1 minus 2, 1, plus 1 over 6, 3, o minus 3, 0, 0, 0, minus 0 over 3, 4 over 6, 1, 1, 1, 1, 1, 1, 1, 1, 1. So 1 over 6, what happens? Minus 1, this is minus 1 plus 3 plus 4. 6, right? Okay, let's just add it. So you add -1 plus 3 plus 4. What do you get? 6, right? 4 plus 3 minus 1, 6. Second one. Minus is 2, right? Plus 4, 6. This is 4 minus 3 minus 1 equal to 0. Okay, this is plus 2, right? Plus 4, 6. And minus 4 plus 4, 0, right? How about the last one? This is plus 2, this is 0, plus 4, 6. This is -1, minus 3, plus 4, 0. Very good. And this is minus plus 2, right? Plus 2, 0, 4, 6. The last one, -1, plus 3, plus 4, 6, right? So it becomes 1, 1, 0, 1, 0, 1, 0, 1, 1, same as A, right? So we can see the aspect of theorem is also working for 3 by 3. So at this moment, maybe I can ask you to calculate this. Just 3. A3, A4, A5. So basically AK is something like this. -1 to the K, lambda 1, lambda 1. 1 to the K, lambda 2, lambda 2. 2 to the K, lambda 3, lambda 3, right? And so this can be your homework. And probably I'll ask you the similar thing like A3 with the kids. So A3 is actually, you can actually multiply the matrix three times, right? And then you can compare with the spectral theorem. So that probably is a good practice for you to carry out the matrix multiplication and check with the spectral theorem. So what I advise you is to find out 5 cases, 5 3 by 3 commission matrix with different eigenvalues. That means lambda 1, lambda 2, and lambda 3 has to be different. I mean, some of the matrices have same eigenvalues for, like lambda 1 is equal to 1, lambda 2 is equal to 1. Those are the cases called degenerate. So this is called non-degenerate case. When some of the eigenvalues are the same, it's called degenerate. But ignore the degenerate case. Just consider the case with non-degenerate eigenvalues. So you can ask ChatGPT, find 3 by 3, or you can actually say Hermitian matrix with non-degenerate eigenvalue. Can you try this? And check it with the ChatGPT. You can find out. See what happens. 3 by 3. So apparently ChatGPT doesn't generate 3 by 3 Hermitian matrices with non-degenerate eigenvalues. So you can actually do it as homework at home. So play with the ChatGPT. Actually, there was one more topic that I was going to cover, but that means extra topic for your quiz. So maybe I can leave for the next week, and maybe I can stop today. What do you think? Okay, so let's leave another material for the next quiz, and I'm going to stop. So the quiz will cover up to here. Great? All right. So good luck with your quiz next week.